Okay, so we did the chain rule and Laplace. We did Fourier series. We did Taylor polynomials and some vector calculus. We did differential equations, and then I think we got down to here. Okay? Now, when I was doing this question, just to get it ready, I kind of noticed a bit of a problem with the way this question's worded. Okay? And it's got to do with the second part of this question. Okay, so I'm going to unpack that, and I actually think that this question will change if it's in this year's test, right? Because it has to change, because there's a sort of something that's not quite right in there. See if you can pick it. All right, so this is a Lagrange multiply question. So you've got a surface, and it's restricted to this line. Okay, and we want to find the extreme values of that, and they talk about the local max and the local minimum, right, into the exact value separated by a comma. Okay, but down here is where it gets a little bit interesting, right? Okay, so yeah. So there's a couple of ways you can do a problem like this, and I showed you one way to do it using Lagrange multipliers way back, like week 2 or something. And there's another really simple way to solve this problem using high school maths. Okay? So let's say you don't know anything about Lagrange multipliers, or you forget, you have a panic attack or something in the exam, and it's like, oh, I just can't do this. I can't channel my inner Lagrange. How might you do this with simpler high school techniques? Any idea? So we're trying to maximize, minimize this function on a line. Huh? I mean, I'm not sure what the surface looks like. X cubed equals x cubed times y cubed. Who knows what that looks like? Maybe there's some symmetry, maybe not. But let's say you've totally forgotten Lagrange. You can't channel Lagrange. What might save you?
You could probably just use simultaneous equation and then just think about it.
I like the idea of simultaneous equations. Thinking about it's also good, right? But even let's get a bit more specific. This is actually a super easy question from high school if you frame it in the right way. So simultaneous equations is kind of okay, but you know, it's not very definite. So this is 2023, T3, and the question is, I don't know what question it is. Let me have a look. Question 5, part B. X plus y equals 9, okay? So a really simple way of doing this is something like that, okay? And then you can think about, you know, differentiating that, setting it equal to 0, finding any turning points, right? And, you know, that's definitely one way to do it. Okay, so if I'm differentiating that, what's going to happen? Well, the 3 is going to come to the front, the derivative of what's in here is going to come to the front, and I decrease the power by 1. Okay? So it's pretty easy to work out where the critical points are if you do it this way. Right? They're going to happen at x equals 0, x equals 9, and x equals 9 on 2. Okay? Okay. So you can take those values and then plug them back into h and see what the value of the original function is at those points. And then you just compare them, right? So, you know, this is the function that we've got. They're our values. So when x equals 0, what's h going to be? What's the value of h of 0? 0, and when x equals 9, h of 9 is 0, and then there's this, exactly what you were talking about, there's this point in between, right? Yep, so. You know, there'll be some other value, right? Oh, sorry. Yep. Okay. So which one's going to be the biggest out of that? Well, the final value will be the biggest, and the other one will be the smallest out of the 3, right? So that's one way to do it, and I would recommend it if it's simpler. I actually think it's simpler. What do you think? Right? Would anybody prefer Lagrange in this situation? No. So why do we have questions like that? It's a pretty friendly question. Right? Now, let's look at another way of doing this. Good morning, Daniel. That is a great, check out that. That is a great good morning. I feel great. Okay, so let's talk about, local minimums and stuff like this. Okay. So the problem with the way this question is worded, we go back. Is that it doesn't actually have a local minimum, right? So this is actually a question where they're trying to tell you something's there and it's not really there, okay? So let me give you an example. How did we work it out? And we're going to go with what you said before, okay? So, I mean, I didn't write this question, but of course we make mistakes sometimes, right? So let's see. You know, people always look at the stuff that I do and go, can't you make it simpler? Can't you make it quicker, faster, easier? So let's go to your idea and see what we can do. Okay? Okay, so I'm going to draw a picture. And I like pictures, even though I'm not very good at drawing. I like pictures, okay? So let's look at the domain of this function, which is basically those points. Okay, so what does this look like? Yeah? When x equals 0, y equals 9. Okay, when y equals 0, x equals 9. So you've got a nice friendly graph there. Okay, so let's look at the points on this orange line, and let's look at what that does to the original function. Okay. So, if I'm in this region here, so I'm somewhere along that bit of the graph, right? And I'm looking at this. X and y are positive there, yeah? In this quadrant, x and y are positive. So if x is positive and y is positive, this combination has to be positive, right? If I go over here, suddenly in this quadrant, suddenly x is negative and y is positive. So what will the sign be of the function? Negative, right? What about down here? Y is negative, x is positive. That'll also be negative, right? And so it's 0 there, it's 0 there, and in between, yeah, it's got to have a maximum. There is no minimum. There is no minimum, right? And so when I read this, I sort of talked to the person who wrote it, and they're like, oh yeah, you know, it happens though. It happens. So even in your exam, you know, obviously you're stressing out and all that sort of stuff. But if something bothers you or there's something that you think isn't right, raise your hand and make a note of it. Tell someone. Because if you don't tell someone, there's no record of it. Okay? Okay? So, you know, what happens if you try to do the second derivative test here? Well, it fails. Right? People go, oh, I'll use the second derivative test. It fails. It tells you nothing. Right? So let me see if I can come up with a picture. Okay. So I'm just going to plot h of x. Okay, so let me pull this out. I'll make it a bit fatter. Yeah, fatten you up. Okay, so look at this. Oops, it's so big it can't even handle it, right? So it's got this massive spike that goes all the way up there and comes down, so there's a bit of symmetry. If you zoom in, there is a line of symmetry, but what's happening at these points? Are they minimums? Yeah, exactly. So you just got to be careful. Okay. All right. So I think what they really wanted students to do there is find the value at the critical point that is the lowest. That's what I think they're actually asking you. Good morning. Yeah, you made it. Okay. All right. So let's see. Okay, that's a pretty big number. And how did we do? Well, it says it's correct, but, you know. All right, so any questions, comments, observations? Okay. Oh, how do you do it using, sorry, what happens if you wanted to do it using using Lagrange? Well, that's okay too. Let me Let me put that up. Right, what happens if you wanted to use Lagrange? No problem, we can do that. Right. If you wanted to do Lagrange, then you would do something like this. Okay, so you would introduce your Lagrangian, f minus lambda g. So that's going to be x cubed y cubed minus lambda x plus y minus 9. Okay, and you're basically finding the critical points of L, right? Or you're solving this problem, grad f equals grad g, right? For some, grad f equals lambda grad g. Now, lambda can be 0 in some of these, but let's talk about it. So if we do this, we end up with the following. So we differentiate that with respect to x. This will become negative lambda. Differentiate this with respect to y. That'll become, yep, lambda on the other side. Okay, and you've got g equals 0. Okay, so based on those three equations, you want to come up with x and y coordinates. All right, so I think the easiest case here is basically to take the first two and put them into each other. Okay, if you move those around, you can cancel the 3. So you've got a common factor of x squared, y squared in both of them. Okay, so if you look at that, x is 0, y is 0, or x equals y. Okay, so in those cases, you would use g equals 0 to find the corresponding points of interest. Okay, so when x equals 0, y is going to be 9. When y equals 0, x is going to be 9. And when x equals y, you're going to get 9 on 2. Okay, so there's 3 options for you. Okay, let us continue. Of course, you would be doing these a lot faster than I would. And I'm just explaining them as I go. And I'm giving you options. Some people don't like options, right? Some people say, I don't want to know 3 ways to do something. I just want to know 1 way. Just tell me what to do. That's okay. Yep.
I'm sorry, I was a bit confused where you got g equals 0 from. I understand like you got the other 2 from the...
Yeah, so the constraint, right, if you go up here, yeah, so that's how we define our constraint. You know, when we're in the Lagrange space, that's all we say, hey, we've got an f, we've got a g, and we set the g equal to 0. Yeah? Mm-hmm. Thanks for pointing that out. Okay? Okay. I mean, what I try to do, the reason I give you like options is because some people like one method and not another method. So hopefully that helps, right? Okay, now, when I looked at this question, it's a system of linear ODEs. I did this in class, right? So I'm going to actually do the Laplace transform version of this. but let me scroll down to that. I'll come back to that if I have time. Okay? Yeah, I'll come back to that if I have time. Okay, so let's look at the Laplace transform problem. I'll put this up for everyone at home. Okay, so we've got a system, a linear system, and you've got some initial conditions. That tells you the value of the unknown functions x and y at one point, t equals 0 in this case. So you've got defined the Laplace transforms. The system can be written as the following matrix form, where A and B, I think, are a matrix and a vector. Okay, so what does this look like, good morning, for this problem? Okay, so let's do that first. Then they're asking you to solve. So come up with the solutions of the transforms, yeah? And then transform everything back. Now you'll see in this question is in quite a lot of the practice questions, right? It's like the numbers and the functions change, but the method and the type of question stays constant, really. So let's talk about that. Okay? So, yeah. So let's have a look. So this is question 6. So both x and y are functions of t. Okay? So what do we usually do when we want to use Laplace transforms on a differential equation? What do we usually do? What's sort of the first step?
Get the table.
Yeah, get the table ready, 100%. Yeah, just...
That's all I have to say.
Yeah, get the table ready. Good. What else? What else have we got? Because we will use things from the table. So what are we going to do to that problem? Transform it. Transform it, solve it, transform the solutions back to the original space, right? So basically, I would apply the Laplace transform to both differential equations, okay? And use the table. Have I got the table? I hope I've got the table. Oh, thank goodness I've got the table, because I can't work without it, right? Okay. So let x of s be the Laplace transform of that solution all right, we're going to take the transform of that side. The Laplace transform is in linear operator. So we can just break that bit up into two transforms. Okay, so the only thing we're really going to touch in this transform thing is the transform of derivatives. Okay, we can do something with that. We want to get these bits in terms of something like big X of S, big Y of S, something like that. Okay, so we go to our table or whatever. Where is the transform of derivatives? Aha. There it is. Now notice the derivative's gone. There, it was over there. Oh, yep. It was over there, but now it's gone. Okay? So let's use that. So this one, number 3, equation 3, will become Sx of s minus x of 0. So that's from the table, from the transform of derivatives tables. This is big X of s, this is big Y of s in our notation. Okay? And we want to do the same thing with the form number 4. Okay? So this is also transform of derivatives. Okay? So what we're trying to do here is solve for big X of s and big Y of s. And then once we've got that, we can enter it into the box, right? And the ultimate goal is to recover the original function x of t and y of t. Okay? All right, so x of 0, that is 3. Y of 0, that is 4. So that bit's going to be 3, that bit's going to be 4. All right, so what we want to do is sort of write this, say, as the following sort of, move things around. It's a linear system, basically. I've got a common factor of x of s and a common factor of y of s down there. So let's see if we can simplify that somehow. So I'll bring that to the other side, I'll bring that to the other side, I'll bring that to the other side. Okay? And let's do the same with the second one. So bring that over there, bring that over there. Yes. Okay? So, linear system. I can solve that a couple of ways. I can solve it using, say, simultaneous equations, or I can solve it using matrices, right? I'm going to do it using matrices. You can do it any way you like. So let's, because we're chasing, if you go back to our question, like, obviously we want to be able to answer the questions here. We're chasing this and this, right? So it's sort of leading you into a matrix representation for your system anyway, okay? So let's see if we can write this as a linear system. Okay? We did it. Now, I mean, you could solve that using, not using matrices, but they obviously want you to do it in a certain way. And if you do it in this way and you invert A, right, you calculate A inverse, you're going to get a nice form because you've got the determinant as part of the calculations. So let's go back to our question. As usual, I can't remember what the syntax is, so there's some guidelines. So over here, let's have a look. Will the preview give it to me? It will. Okay. So that's going to be your matrix A. It depends on S, but that's okay. And this is going to be your matrix B. Okay, so there it is. All right, questions so far? So with these kind of problems, when you're given a differential equation, take the transform of everything. That's it, right? Yes, boss.
When you at the start, you converted. I get what you did with the Laplace for the left side, but why did the right side just become x of s and minus y of s?
So let's go back to the working. Okay, so guide me here. Where are we?
Pretty much the let, pretty much. Let x of s equal to L of x.
Yeah, so this is just notation. So I'm defining this. Right? I'm saying instead of mucking around with 3 things, let's just use 2. Okay? Yeah? Yeah. So that format that I've just boxed up, it emphasizes that when you transform something, you're going to get a function of s.
And what it isn't important. It's just a function of s.
Yeah, well, it's the transform of the solution.
Yeah.
So if you can find the transform of the solution, you've half solved the problem because you can untransform that and recover the solution to the original problem. Yeah. It's convenience, really. Yeah, or simplification. Okay. And I get it, right? Because remember learning vectors in first year, right? You can write a vector lots of different ways, as a column, as something with boldface, a arrow, whatever. It's confusing, but sometimes it simplifies things. Yep. Okay. So let's see what's just happening at home for a sec. Good morning. Okay. So solve. Sorry, let me put this up for people at home. Solve the previous linear system of equations and enter the expression. So what we're trying to do now is solve for the transforms of the unknown functions that solve the differential equations. Okay? So how do I do that? Well, I need to go, let's just do it here. If that's my system and I'm looking for big X and big Y, I want to find the inverse of that matrix A, right? If I'm going to use matrix methods, which I think that's what they're trying to tell us, let's compute the inverse of A and then multiply, and that's the solution, okay? So, if I'm down here and I want to get rid of that, right? Can anyone remember how to compute that inverse of a 2x2 matrix? What do you do? I'm not talking about row reduction. Let's just leave row reduction behind in first year. What do we do? Inverse of a 2x2 matrix. I mean, you can solve it using simultaneous equations. That's okay. But if you wanted to do it, what would you do? Okay. It involves determinants, right? So if this is, say, your matrix A inverse, okay, so you switch those two and you change the signs on those two. Okay? Let me say that again. You switch the positions of those two and you change the signs on those two. And you divide by the determinant. Okay? Right? So they're the same, so it's not going to change the main diagonal. You change the signs on those ones. And you need to divide by the determinant. So how do we calculate a determinant again? Confused. 2x2 determinant. Yes, come on.
S minus 1 squared plus 4.
Yep, exactly. So with a determinant, you're working diagonally, yeah? So the determinant of this matrix is that times that minus that times that, okay? Okay. So now, oh, you made it. Hello. Where are you going? Did you just arrive? Yeah, welcome. Okay, so if I'm using these methods, I would just multiply both sides by the inverse matrix. What did I do wrong? That times that minus, plus. Dankeschön. Okay. Yep. So that's it. Right? That is it. And so you can, expand this out. And you're going to get something like this. Okay, so this is going to work on everything. So 3 times that. There you have it. Okay, so x of s is going to be that divided by that. Big Y of s is that divided by that. Now, if you notice, I've been quite careful with not expanding brackets. Does anybody know why? Why have I left the s minus 1 all squared together there? Because my daughter does the same thing, right? She's in year 9, and we have these arguments about expanding brackets, and she goes, "You should always expand the brackets." I'm like, no, not always. What do you know? You don't know anything. That's another story.
Is it got to do with keeping the shifting theorem sort of intact?
Yep, exactly. Notice that there is s minus 1 and s minus 1, s minus 1, s minus 1. It's a shift. It's a shift. And we're going to have to undo that later. So there's, people come to me during the break and they say, "Oh, what's wrong with this Laplace transform?" And I can't just look at it and go, "Oh, that's wrong," because the form is not a nice form like we have here. They've done something to it, right? So don't expand the brackets if you don't have to. Okay, so big X of s is this. Big Y of s is that. Put them into the computer. That. Okay. See? Don't simplify it, Mobius. It's a trap. Okay, good morning, hello. You made it, well done. All right, so questions so far. We've only solved half the problem here. We've got to get back to the original space. We feel good in the transformed space because we've got big X of s and big Y of s. Now we have to get back, right? So how do we do that? Well, we're going to use the inverse transform on these things. Okay? So let's actually write them out and see how we go. If I can find my pen. Oh, yeah. Okay, so let's bring that out. Got to stuff it up, don't I? Okay. Just pretend that didn't happen. Okay. Okay, I'm going to write the falls as 2 squareds because that might be helpful. Okay, so this is the challenge now. We have to find the inverse transforms. That's a negative 12, by the way. The inverse transforms of these things. So what's the easiest part to start with first? If you were given this problem, what are the easiest bits to find the inverse transforms of?
The terms without the s minus 1 in them on the top.
Yeah, well, I mean, I would probably start with, I would start with no s minus 1 in the top. Is that what you're saying? Yeah, exactly. The term with the 4 up the top and the term with the negative 12. Exactly. Okay, so I would start with that one first and that one. Okay, so let's have a look at our table. Fit it. Is there anything in that table that will help us there? Sort of. So let's say you wanted the inverse transform of 4 on s minus 1 squared plus 2 squared. What do we have to manage there? What do we have to navigate? Hang on.
We can take out minus 3 and use w over s squared plus w squared.
Mm-hmm. Yep, you're right. So this is a bit like that. But not exactly. What's the difference? Well, the w, or the omega and the omega aren't the same. And instead of s, you've got s minus 1. Sounds like a shift, right? So before we get to that, we go down here. Okay? So this is one of the shifting theorems. Okay, so it's a 2-stage process. We're identifying something in a table that looks a bit like what we have, but it's not exactly. To get there, we can use a little bit of algebra, but we're going to have to use a shifting theorem. All right, let's take a 10-minute break. We will come back. Okay, everyone. It's very sad. It's the final lesson together because remember what's happening on Friday? It's a holiday. Right? It's a holiday. So lest we forget the holiday, right? So don't come on Friday afternoon to the law building because I won't be there. I'll be enjoying my holiday, okay? You should too. Okay, so I'll do this one and then I'm going to do a PDE one, which you haven't seen yet in lectures. Somebody asked me about it yesterday. But let's untransform everything, okay? So it's the first shifting theorem. That looks like that looks like that looks like that. And in all of them, A is equal to 1. So we're going to apply the first shifting theorem 4 times. Okay? So we just need to work out what the big F's are for each of the parts. Okay? Now that 3 is going to be out there. Okay, that 2, it's going to be a bit like that, but that's not equal to 2. So I'll bring a 2 out of that, just to make it nice and easy. With this one, I can take a -6 out of there. And over here, I've got the 4 out of there already. Okay, so first shifting theorem. What's the first term going to be? Well, the first shifting theorem tells us that if I've got a function of s that's been shifted alpha units, take the inverse transform of big F of s and multiply it by an exponential. Okay? So for this one, cover up the -1. What does that look like over here? It looks a bit like that one, right? With with omega equals 2. So the transform of that will be sine of... Oh, hang on. Actually, let's go up here. Do that one first. So I'm going to cover up the -1 and the -1. It looks a bit like this one. Yep. So that's going to be a cosine. All right, that and that. And the other one's going to give you a sine. Okay. So it's going to be 3 times an exponential, because remember the inverse transforms a product, times either a cosine or a sine function. Okay, over here, this is going to give you essentially an exponential times a sine function with the 2 out there. Okay, down here, well, that is pretty much the same as that, so we're going to get the same thing as over here, and you multiply by -6. And over here, this is basically the same as that. So you're going to get the same transform over there, just multiplied by 4. Okay? So the first shifting theorem's at work. If you get halfway, get big X of S, big Y of S, that's part of the journey. You can get some marks for that. And then you untransform everything. Okay? Questions? Okay. Oh yes, hang on.
Would you need to do t minus 1?
So that's a good question. So for this thing, let's have a look at the form of those things. So so if we go back to our first shifting theorem, the shift's there, but there's no shift there. Okay? So in this case, alpha is, oh, alpha's negative 1. Hang on. Blah, blah, blah. There. Is that what you're worried about? No, because see how there's no shift? It's just t. Yeah. So, yes, but that's, yeah, alpha equals negative 1, not positive 1. So you found another mistake. Any other questions? Any other questions? Wait. Thank you. Oh, sorry. Hang on. I can. Yeah, it's all part of the 5-star the 5-star service. All right. So look, I'm going to do a problem now that is very important. Okay. It's going to be a PDE one. Okay. I'll just flash this up. I'll come back to that if I have time. But this is an important problem. So let's go here. All right. So this is called Laplace's equation, named after the French mathematician Laplace. Okay? And it looks suspiciously like the wave equation, right? But it's not quite the wave equation. The wave equation is similar in the sense that you have second-order derivatives. The heat equation has a second and a first, but the wave equation would have a negative sign there, and this one is a positive sign, okay? They also talk about steady state temperature. So basically you've got a rectangular bar or something, and each point in that bar there's a temperature. It's two-dimensional. What do we mean when we say steady state? Does anybody know? If I talk about a steady state. Anyone? Yeah. Hang on. I'll come. Oh, you okay? Can I get that one too?
It's an equilibrium.
Yeah. So one way to think about this in this context, and you're right, in the sense that it doesn't depend on time. Yeah. So in this case, x and y are spatial variables in a two-dimensional rectangle, and time, the temperature is independent of the time, which is, I think, what you're saying, right? Yes. Okay. So you've got some boundary conditions on the edges of the rectangle, and you're told that the temperature along those edges of the rectangle is 0. Okay, but inside the rectangle, the PDE is taking over and stuff is happening. Okay? So there's a list of boundary conditions, and then you're asked to use the method of separation of variables. Now, we've done the heat equation and we've done the wave equation with separation of variables. The method doesn't change. Okay? The method doesn't change. It's just that, this problem has a positive sign, whereas the wave equation has a negative sign. So you just need to keep track of these small little changes. Okay? So let me show you how you can solve this kind of problem. Okay, so, you don't have to do this, but I'll just draw a little picture. Right, basically you've got a slab. Yeah, and this is like pi on 10, right? And this is not drawn to scale. That's pi. Yeah. So along these boundaries, Along the edges, the temperature's kept to be 0. And then in the center, or like not on the boundary, this is where the PDE holds. Okay? So it's spatial, it's not time dependent. Okay? All right. So let's have a look at how you apply the method of separation of variables to this problem. All right. So the basic idea is to say, okay, I'm going to assume that the basic form of the solution to the PDE is a product of two functions that depend on different variables. Okay? So what do we do now? Who can remember? Who can remember what we usually do with separation of variables? What would we do now? Anyone? If we're solving this problem, what would we try to do? How might we determine big X and big Y functions? Anyone? 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 Yeah. Oh, no. We do something to big X and big Y. If this is a solution, oh, actually, hang on. Let's use the same note. So they've used big F and big G. So let's use that notation. Okay, big F and big G. If this satisfies this, what do I know about big F and big G? What are some equations? Yep. So if I compute the derivatives that appear there in terms of those things, I'm going to get something like that. Okay? So let's try to do that. So if that's my guess, and I want that, it's going to be, yeah, because this bit doesn't depend on x, so I'm only differentiating this bit. Well, that's ordinary derivatives. Okay? So if I was to substitute those forms into there and separate the variables, I'm going to get two sets of equations. One is for f and f double prime, and the other is for g and g double prime. Okay? So let's try that. So we take those, sub them in for this derivative and that derivative, and we'll get something like the following. Okay, so I'm going to get f double prime g plus f g double prime equals 0. So that's what this thing becomes. So separation of variables. It's called that because what do? We separate the variables. Okay? Makes sense? So let's do that. Okay, and then let's pull these apart and see what happens. Okay? So I'm going to pull them apart. I'm going to say, okay, f double prime over f equals g double prime over negative g. I'll just put the negative sign down there. Okay, so basically I've just moved bits of that equation around. And what do we notice about this? Well, f depends only on x. G depends only on y. So what can we conclude about these ratios? What can we conclude about these two ratios? They both equal a constant. That's called the separation constant. Because if you vary x, you're varying the left-hand side, but the right-hand side isn't varying. So how can you vary one side and not have the other thing vary if they're equal? The only explanation is you have a separation constant. Okay? I'll call it K. Separation constant. All right. So now we have a challenge. And it's quite a nice question. It's a multiple choice, right? You can guess at the very worst case scenario. Yeah. Choose the correct pair of ODEs that F and G satisfy. Well, if I'm going to pull these apart, let's use this K. And so F double prime equals KF. G double prime equals negative Kg. So that'll become those. Okay? So it's going to be the second situation. Yep. So you don't have to write out everything that I've written out. You don't have to draw a picture if you don't want to. It's completely up to you. They're asking you for the forms for F and G. Okay? Questions so far? Let's have a look. Missing a 2. Oh, am I missing a 2? Oh, I'll come back to that, Samuel. Okay, Samuel says I'm missing a 2 in the sine term of x of t. Okay, just make sure I've written that down correctly. Thanks, Samuel. Okay, so that's actually a pretty easy question. Only one of these things will be correct. So, you want to go for that form. Okay. Okay, so let's turn over. Oh, boundary conditions. All right. So if I just go back to my internal computer, the next part of this question is the boundary conditions for G of Y. Okay, this is again a drop-down list. So let's have a look at the possibilities. Okay. There's a bunch of stuff, but how did I get that? Well, I go back to my original form. Yeah, there. And I use some of the boundary conditions. That boundary condition and that boundary condition. Okay? Because they involve the y component, and we know they're equal to something. All right? So what would we do if we were doing this ourselves? Well, we would look up here, use these two conditions together with this form. Okay? Okay, so if we look at this, you don't want big F to be identically equal to 0 because that's not an interesting solution. So G of 0 is going to be 0, G of pi is going to be 0. Okay? Not too difficult. Just got to keep track of things. So we've got this equation, and we've got those boundary conditions. We're going to solve 3 cases now, and the question, it leads us through it, which is nice. There are 3, actually I'll put it up here, people at home. Okay, so we've got that, all right. So there are 3 situations. Select the solution for each case. Okay, so for this problem, the first case is k equals 0. So what will happen? If k equals 0, that term disappears, right? So it's g double dash equals 0. So we can integrate that twice. Yeah, we integrate a y plus b, something like that. And then you have the boundary conditions. Okay? So, for this case, k equals 0, this problem becomes g double prime equals 0. Okay? Now the only numbers a and b that satisfy this thing and the boundary conditions are a equals 0. Okay? So in that case, it's just the uninteresting, trivial solution. So we don't care about that. Okay? In the second case, they go, oh, okay, well, what about when k is positive, right? So we're looking at this problem with these boundary conditions when k is positive. Okay? And in the second case, we're looking at it where k is negative. Okay? So they've introduced this omega squared just to make the notation look a little bit simpler. Okay? So what happens in this case? Well, we might get the 0 solution, but we're actually not. So let's try it. Okay. What are the roots of our characteristic equation going to be for that? They're going to be real and equal, they're going to be real, they're going to be complex. What are we going to get? Everyone's like looking away. It's like don't maintain eye contact. So there's 3 choices. Are they going to be real and equal, real and unequal, or complex? Complex! Yes! Dankeschön. Okay? So, in this case, G is going to be something like this. Okay? And let's find A and B if we can. So G of 0 is going to give A equals 0. And then over here, we get this monster. And this is where the action happens. Right? We don't want B to be 0 because that's not very interesting. So when is sine omega pi 0? It's 0 when omega pi equals pi, 2 pi, 3 pi, 4 pi, etc. Okay? So it's starting to get a little bit heated now. All right, we get a sequence of solutions. So, which one out of this mess is going to give us the solution? Well, it's going to be that. Okay, so I've just basically replaced omega with n, and I've put a sequence of constants here because there's a infinite number of solutions here. So that would be the right one. Okay, so now you're thinking, oh my God, there's another case to consider. I'm tired, I want to go home. Only one of the three cases will give you something interesting. So in the third case, just forget it, right? It'll just be 0. Okay, yeah. So in the third case, it's just going to give you 0. So don't need to spend any time on that. Okay, so we've got a sine series, or a sequence of sines here. Solve for f of x and express, so we've got g of y, solve for f of x and express this as a series that is like that. C naught is going to be 0 determined by the boundary conditions here, okay? And so what are you going to get when you solve for big F of x? Well, look in the box, right? You've got the sine, the sequence of sines here, which is we just calculated, but now you've got a sequence of shines. Sines and shines, all right? Sine and sine her. So where does that come from? Okay, well, we would go back and solve that case when k is positive, because that gave us the interesting situation. Okay? So for this one, you would solve that okay, so what are the solutions of this going to be? The sign has changed now. It's a negative n squared. Okay. Okay. The no sleeping rule still applies. Just for another 20 minutes. You can do it. Okay? So, what is the bottom differential equation? What is it? What are the solutions going to be? Well, the roots of the characteristic equation are real and unequal, so you're going to get exponentials, right? Exponentials. But that doesn't look necessarily like shine. So where does that come from? Well, we'll get there, don't worry. We'll get there. Okay? Okay, and in fact, you can sort of think of these as sequences here. Okay? All right, so what haven't we used yet from our information? We haven't used this, right? We've used that, we haven't used that. Okay, notice it's in the conditions in X, not Y. So that's something we want. Okay? Okay, so we want to put in x equals 0 and get 0 up here. So what's going to happen? Well, this is going to become 1, this is going to become 1. So the only thing we can really say about these constants Cn and Dn is that they're the negatives of each other. Okay, so let's go back up here. Replace, say, Dn with negative Cn, and you're going to get something like shine now. Okay, that's kind of like shine. You just need the negative, the 2 in there. Okay, so En will be Cn on 2. Okay, we can define all these constants that, it doesn't really matter. All right, so we have got, what have we got so far? We've got that. We've got that. What are we going to do? We're going to multiply them together and add them all up. Okay? But this is where this format comes from, right? So in this case, Cn is going to be, I don't know, Bn times En, okay? So we take that, multiply it with that, and this constant's out the front. Okay? Questions? Yes?
I have two. Firstly, why is the f0 equal to 0?
Okay. Excellent question. Right? Why is that equal to that? Well, let's look at our data. We've used that. What does this mean in terms of this and this? So we're going to go in here, say x equals 0, and set this product equal to 0. Okay? The only way this product can be 0 is if one of these things is 0. It can't be that, it's got to be that.
It can't be the gy
Because it's not interesting. It doesn't give you... The only thing you'll end up with then is big F equals 0, big G equals 0, which 0 solution is not something you want. Okay? Okay? So... Oh, there's another question.
Another question. Yeah.
Oh my goodness.
Why do we multiply the two solutions together?
Because, remember, we start with this form. And so you're multiplying together. But the thing is, we don't just get this nice little form. We get a whole bunch of stuff like that, right? We start very simply. Go, let's just assume it's of this nice form, right? And then it goes batshit down later, and you get an infinite number of solutions. You're just multiplying each bit together, okay? And then we add them up, right? We add them all up. Other questions? Yeah. Thank you. Okay, so that's where this format comes from, and that's why the shine is there. Now, why did I change it? Why didn't I just leave these as exponentials? Well, if we go over here, the very last part of the question. Right? This is finding the CNs. Okay? Finding the CNs here. Where are we? There. Okay? So if we have that, we compare it with that. Okay? So let me see if I can find my notes for that. They're here somewhere. Just give me a minute. Ah. Okay. Well, I don't have the notes for the last one, but essentially what you do, yeah. So what you do is, you've got this product of this with this, you got that, you add them all up and then you compare them with this, okay? So basically you're adding up, you're writing out some of the terms of the series, right, for this, and then you're comparing them with this. So obviously n equals 7 and n equals 9 is super important, okay? And there's only two terms in your solution because there's only two terms here, okay? So that's how I did that. Okay, so if you get to that point, you're probably feeling pretty happy and you're feeling pretty exhausted too, I would think. I do when I do these problems. But for part D, you're just taking your above crazy sum, you're putting in x equals 0, and you're comparing it with what h of y is. And then you're choosing the coefficients. There's only two to choose here, right? Questions? Thank you, Zach. All right, so how did we do? Did we get it right? Hopefully I've got this all right. Oh no. Okay. I'll delete that. Okay. So sum that up, compare it with that. Okay. What's the answer? Hang on. I'll just show the answer just on the thing because it'll tell me. Won't it? Yeah. Hang on. Oh, how can I scroll across? Maybe I'll make it smaller. Oh, how can I? Oh yeah. Come on. I can't go across. Anyway, you get the idea. The coefficients have basically got what I had, but you're dividing by sine of 7, 10 pi. Okay? Now, what's down here? The text boxes in this year is basically, you can provide your methods for part C and D. They will be marked manually in case you make a mistake. So if you make a mistake and you're frustrated and you're freaking out, you can use that text box to vent, right? Or just provide some working or whatever. Yeah. Yeah, exactly, right. So I remember we asked somebody, explain why this formula's true and how you solved this problem. And someone put, yeah, because I'm Batman. Right? I don't think they got any marks, but yeah. Yeah. People read it. I'll read this. If you write something here, I'll read it. No. Oh, good. Very good question. So how do you use the text boxes? So I would use sentences, okay? I would use sentences and simple things. So, something like that, right? The k is the separation constant. You don't want to have lots of equations. And I mean, you can use the editor if you want, but I mean, come on, where is it? Okay, who wants to do this, right?
If you write in equations, do you have to use the equation editor?
No. I wouldn't do it. I just wouldn't use the equation editor. But if you want to, you can. I would use words first and try to be as simple as possible, right? And some people go, well, that's why I did engineering, to get rid of and away from words and English, right? But it's helpful if you can say something, okay? And then question 9 is the end of the exam. Yay. All right, so I'll do one more, and then somebody asked me about this yesterday, and I was shocked. Aha, this one. Okay, I found this one a bit strange because it's a non-linear differential equation. The first one is non-linear. And so, what do? Okay? But the hint is important. It says solve for y of t first. Okay? So I'll just show you a little trick with that. So just give me a minute. I'll switch over in a second. Okay. Okay. All right, so this is our problem. Why do they say solve for y of t first? Yep. This one's super easy to solve, right? Who knows what that is? But if I can get y from there, then I can sub it in there. Yeah? So let's try it. What's the solution to this one? Well, it's something like that, where b's a constant. Okay? You don't even have to justify that. You can separate it if you want, but who's got time for that really? Not me. Okay? So what you would do then is you would go up to your original equation and, well, actually you can calculate what b is from here. Okay, so b e to the 0, that's just going to be b. Okay? So in this case, we did what we were told. So let's take that y of t and sub it into the original, the first differential equation. Okay, so take that, put it in there. Okay, so the 4 divided by 200 will be 1 on 50, and you're going to get something like this. Okay? And this is not a difficult problem to solve either now. Okay? It's linear, it's separable, but also you can just solve it directly. Yeah? If you have something like this, yeah? So for some f of t, yeah. You can just do it like that. Okay? So this one's pretty easy to solve. You just got to keep track of all the exponentials. Okay? So once you've done that and you've put in the initial condition, you will get that. I mean, we already had that, and we'll get that. Okay, so you've got an exponential with an exponential inside it, which is a little bit annoying, but I don't think you can get around that. Okay, so that's how you do a question like that. All right, folks. Well, I think it's time to finish. It's very sad. There's something in my eye. I think I told myself I wasn't going to cry, but I will miss you. Good luck. Right? Good luck. I know you can do it. I've really enjoyed the lectures, and thanks for being part of it. And you know, like, if you see me, come and say hello. You know, I see people walking around uni, and I know they're in my class, and some of them just like